My name is David, and this is the proof method digital logic exercise. For the exercise, we were asked to create a Python program to prove whether if a number n is prime and 2 to the power of n minus 1 is prime as well, then 2 to the power of n minus 1 times 2 to the power of n minus 1 is a perfect number. Let me run you through the program. The program begins in main, where we check that values for num 1 through 20 are prime numbers. To do this, I created the isPrime function that receives num to check whether the number is prime. Because a prime number only has divisors of 1 in itself, I decided to create a for loop to iterate through the rest of the numbers, these being 2 in itself minus 1, because any divisor in this range would imply that num isn't prime. To make my code more efficient, I decided to iterate until the square root of num, as all the numbers until the square root pairs would also have included the rest of the divisors. For example, for the number 36, by covering the divisors until 6, the divisors being 2, 3, 4, and 6, we would also have covered the numbers 9, 12, 18, and 36. Note that we simply cover divisors until the square root of 6. After this, we checked if num divided by any of the I values resulted in a remainder. Essentially checking if any. After this, we checked if num divided by any of the I values results in a remainder, essentially checking if any of the I values would be a divisor for num. By doing so, this would imply that num is not a prime number, otherwise it would return true. We then go back to main to assign 2 to the power of n minus 1 times 2 to the power of n minus 1 to k for each value of I, and then check whether it is a perfect number if 2 to the power of n minus 1 is a prime number. We do this by calling the isPerfectNumber function, which receives the value. For this function, I created a list consisting of an element of value 1, and this value 1 is assigned to the variable sum. I created this variable to track the sum of the divisors to then compare it to num to see if they are equal. We then iterate through all the values to check whether I is a valid divisor, to add the divisor to the list and update the sum value. We also consider the pair of the divisor and then add the pair to the list as well. Finally, if the sum of all the divisors equal to num, we return true as it is a perfect number, the list of the divisors and the sum, or else return false, the list of the divisors and the sum. Going back to main, we simply print out the number 2 to the power of n minus 1 times 2 to the power of n minus 1, the divisors, the sum of the divisors, and whether the number is a perfect number. This is done to perfect numbers that prove the claim for prime values less than 20, whose 2 to the power of n minus 1 is also prime. Running the program for each n value, we have the product of 2 to the power of n minus 1 times 2 to the power of n minus 1, its divisors, the sum of the divisors, and whether it is a perfect number. Before ending this video, I want to mention the preciseness for these Marasian prime numbers. The fact that a number and the sum of its divisors are equal show the character and identity of God in this very creation. Not only does he have specific and grandiose qualities, but as Romans 1 says, his divine qualities have been revealed to all of humanity. This perfection of perfect numbers are a glimpse of his character, of divine order, and of his wholeness. Thank you for watching.